So what I want to do is I want to go through questions, and if you added a question this morning and it's not on here, I'll go back through those and make sure that I answer additional questions tomorrow. So questions that I saw from video 7.3. So this covered weak acids and weak bases. One of the questions was, can you talk more about ionizable protons? So remember when we're talking about protons, we're talking about H+. So an ionizable proton is a proton that is donated from an acid. So when you have HCl, that first hydrogen, that's an ionizable proton. HCl can donate back to a base. Usually it's the first hydrogen in the formula unless it's an organic acid. And we'll look at that example when we look at number 21 of mastering. And we'll look at what happens if we have an H at the end, what that would look like. Another question was H+ versus H3O+, because in the video I went back and forth. They are the same thing. H+ is a shortened version of H3O+. H+, we just are not incorporating the water. Because when H+ is added to H2O, we get H3O+. So they are one and the same. If you see something say H3O+, but you have H+ written down, that's okay. It's the exact same thing. So you can write either one, whichever one works for you. Again, we're going to look at an example in mastering where they want us to focus on each one. Appendix D, we'll be using Appendix D throughout these examples, especially as we get to some of the later examples today and the examples tomorrow. So Appendix D, all right, if you take a look at Appendix D, what it has is it has the name of the acids, it has their formula, and then it has the Ka values. So Ka is the equilibrium constant for the acid at equilibrium. Now, some of them have multiple Ka values because they have multiple hydrogens. So if they have, in the case of like arsenic acid, is H3ASO4, it has 3 ionizable protons. It's called a triprotic acid. So it has 3 Ka values. We're going to look at an example tomorrow of a polyprotic acid, meaning it has multiple hydrogens. And we're going to look at how to know which Ka to use. We're going to look at that tomorrow. But on the back, at the top, we have Kb values. So Kb, all right, that's the equilibrium constant for a base. So at the top, we have Kb values. And then table D3, we're going to look at that in the next unit. So these are all different equilibrium constants. Ka is an equilibrium constant for an acid. Kb is an equilibrium constant for a base. You will be given Ka values on the AP test if you need them, which means you'll be given them on quizzes and on tests as well. When we do calculations this unit, because we're focusing on equilibrium, we'll need Ka values when we want to use ice tables. That's why Appendix C is useful. If we need to use an ice table and we need a K, right, whether it's Ka or Kb, we can use Appendix D. Now, something that we're going to hit on again as we get into examples is when we have very small values of K. So very small values, something less than 1 times 10 to the negative 4th, we can neglect X. Right? We can ignore X, or we assume X is small, and this prevents us using the quadratic formula. We should never have to use the quadratic formula in this unit because we can assume X is small. And then the last question was about Ka times Kb equals Kw. This is on the equation sheet. Ka times Kb equals Kw. No matter what, that equation holds true. But remember that Kw can change as temperature changes. So if you're at 25 degrees Celsius, Ka times Kb is 1 times 10 to the negative 14. If you're not at 25 degrees Celsius, they would have to tell you what the other Kw value would be. They always have to give you the information that you would need. And as we go through, we'll really cover a lot of these things. So I want to go through number 21 of mastering. So this is not in your notes. If you have like a separate piece of paper that you want to write this down on, the reason I want to go through this is because of the questions that there were on the video. A about H plus versus H3O plus. And so I thought, I was trying to look through mastering to see if there was a question. And 21 is this. So again, this is number 21 on mastering. Now, will your acids be the same? Maybe. All right, it all depends. So in number 21 of mastering, you can see part A and then part B, and then I just pulled out C, E, and G. For this, it wants us to show the reaction of a weak acid. It wants us to show what happens to a weak acid. And so part A gives us HBrO2. And it says show the reaction with H plus as a product. So HBrO2, show the reaction with H plus as a product. So we're showing what happens when we put a weak acid into water. So HBrO2 is a weak acid because it's not one of the 7 strong. So I'm going to have HBrO2. All acids are aqueous solutions. Now, because it wants us to show the reaction with H plus as a product, we ignore water as a reactant. And because it's a weak acid, it's at equilibrium, so we need a double arrow. We're showing the ionization of this weak acid. So the ionization, we're going to break this weak acid up into its ions. H plus and BrO2 minus. Ions are always aqueous because ions come from an aqueous solution. So the ionization of this weak acid with H plus as a product, we have the weak acid at equilibrium with the ions. And then part B says write the Ka expression for the ionization of this weak acid. Well, remember that the Ka, so this lowercase a, just means that we're writing the equilibrium expression of an acid. That's all that A stands for, is that it's an acid. So it's still products over reactants. An equilibrium expression is always products over reactants. We never include solids or liquids. So we're going to have H plus concentration, BrO2 minus over the weak acid. So that's our Ka expression. The way it works on mastering is that parts B, D, F, and H are actually multiple choice questions for writing the K expression. So then part C says, show the reaction with the hydronium ion as a product. When we have H3O plus as a product, that means that we need to show water in the balanced equation. So in part C, we're going to have HBrO2. Remember, acids are always aqueous, plus H2O. Water's a liquid. Still is at equilibrium. So this is actually the full ionization equation. The actual ionization equation shows the acid reacting with water. Right? And by reacting, the acid is donating its proton to the water. Water is accepting the proton. We shorten it by just doing what we did in part A. What it actually is going to look like, the H plus is going to donate to H2O, and water is going to become H3O plus. And then we're left with BrO2 minus. So this is actually what the ionization looks like. But we simplify it by saying H plus is the same as H3O plus, and then we can ignore water. Now when you write the K expression, here's where you have to be careful with your K expression. It's still products over reactants. So H3O plus times BrO2 minus. But make sure that you're paying attention to all of your states of matter. because water is a liquid. We don't include liquids. So it's actually just going to be over the concentration of HBrO2. Right? Again, because this is a liquid, we don't include liquids in equilibrium constant expressions. And then parts E and G are similar, except we have a different acid. So I wanted to show you this one because this is classified as an organic acid. So we have C2H5COOH. The H at the end, the single hydrogen, is actually the ionizable proton. We're not going to take a hydrogen out of the 5 H's. We're going to take it from the end. So in part E, show the reaction with H plus as a product. So it's just like what we did in part A. So C2H5COOH, acids are aqueous, is at equilibrium with its ions because we just want H plus as a product. So we're simplifying. So we're going to have H plus. Now when we remove the H plus from this acid, it's going to be C2H5COO minus. We're taking the hydrogen off the end. So we're taking the H plus away from the end. And then part G is going to be similar, except we have to include water. So C2H5COOH, acids are always aqueous. Now we're going to show the full ionization, so we're going to show it with H2O. So C2H5COOH is going to donate its proton to water. Water is going to become H3O plus. Ions are always aqueous. Plus conjugate base, C2H5COO minus, which is aqueous. In, what is it, what? GH, part H, when you're writing the K expression, like, don't forget, liquids do not get included. These are representing the same thing. It's just in part C and part G, we're showing the full ionization with water. You can do shorthand like we did in A and E and still be okay. Right? H plus and H3O plus mean the same thing.
Why is there a double arrow?
Since these are weak acids, they're at equilibrium. So even though it is partially ionizing, partially is the key word there. So like for any of these, since these are weak acids, right, only about 5% ionizes. So that means that we have some reactant, or we have mostly reactant, and some product. So it's going to be at equilibrium. Strong acids, because they completely ionize, have a single arrow. Yeah. So example 13, now we're getting into equilibrium. We're getting into ice tables. So if you didn't like ice tables, sorry, but we're going to keep doing them. So example 13 says a 0.2 molar solution of niacin. And it says it's a monoprotic weak acid. So we don't even need to know what the actual formula of niacin is. That doesn't matter. But it says it's monoprotic. Mono means one protic proton. A lot of times we'll just be using this general equation. HA represents an acid. H plus, A minus is some conjugate base, some ion. Doesn't even matter what it is. So it's just a monoprotic weak acid, has a pH of 3.26. What is the Ka for niacin? So I want to go through this and just label some things first. When they give you the concentration, a 0.2 molar solution of niacin, when they give you the concentration, that is the initial concentration of the acid. So when they give you the concentration, it's the initial concentration of the acid. If they give you the pH The pH actually tells you the H plus concentration at equilibrium. So the pH of a solution is the H plus concentration at equilibrium. Now, when we go through and we work with weak acids, it's important that we remember that it's at equilibrium. So the first thing that you want to make sure to do is write down the acid dissociation equation. I know that this is an acid, so I will be using Ka. Now in this case, it wants me to solve for Ka, but there are times when we're solving for something else. So I like writing Ka over here just so that I remember that this is an acid. It's an acid equilibrium problem. So since we're at equilibrium and we don't really have much information, we know we're solving for Ka. Right, we know at the end we are eventually going to solve for Ka. I'm going to leave some space right underneath this. So leave some space right underneath because we're going to write an ice table. But what I want to do first is I want to write the equilibrium expression. So let's write the equilibrium expression, the Ka expression. Equilibrium is products over reactants. So H plus times A minus over HA. So in order to calculate Ka, this is an equilibrium expression, so we need equilibrium concentrations. So we need to know what are all of these concentrations at equilibrium. Well, to do that, we can use an ice table. So I know initially I have a 0.2 molar solution of acid. Remember, the only thing that can go in an ice table is molarity or pressure. I have nothing else. It doesn't say anything about having ions. Now, really quick, pH. Remember that pH is negative log of H plus. If we're given pH, we have to do the inverse. So if we have pH, the H plus concentration at equilibrium, pH gives us at equilibrium, is 10 to the negative pH. 10 to the negative 3.26. So if I do 10 to the negative 3.26, 5 point, I'm going to keep it out to a few sig figs, 495 times 10 to the negative fourth. There's our H plus at equilibrium. So right now in our ice table, we have the initial concentration of the acid, and we have the equilibrium concentration of H plus. If you have the initial and the equilibrium of one of the substances, you can figure out the change row. So I know that H plus, to get from 0 to its equilibrium concentration, we added 5.495 times 10 to the negative fourth molar. Because it's a 1:1:1 ratio, that means that A minus increased by the same amount. So its equilibrium is 4.95 times 10 to the negative fourth molar. And because HA is on the other side of the arrow, it decreased by 5.495 times 10 to the negative fourth molar. Now, if we do 0.2 minus this value, we get 0.199 molar. And if I went out to 4 sig figs, 0.1995. Now, the equilibrium concentrations are what are important when we want to plug into Ka, because K is equilibrium constant. So I can do 5.495 times 10 to the negative fourth squared, because it's the same thing, divided by 0.199. 5.495 e negative 4 squared divided by 0.199. And technically we have 2 sig figs because we have 2 sig figs here and 2 decimal places. 1.5 times 10 to the negative 6. Remember that K, equilibrium constants, do not have units. They are just numbers. Oh, remember when we talked in our last equilibrium unit that the value of K tells us what is favored at equilibrium. Because K is so small here, remember that this means that reactants are favored. And so with reactants being favored, that means that at equilibrium we have mostly reactants, which is true of a weak acid, because weak acids only partially ionize. So it makes sense that our Ka values for weak acids are going to be very small. So when we're looking at this example, again, it's important that concentrations that they give us, those are initial concentrations. pH allows us to find H plus at equilibrium. And then this example, if you didn't add this, this is like number 22 on mastering. A lot of these questions that we're going to do are similar to many different ones on mastering, but I just tried finding the ones that are most like it. Questions on this before we look at the next one? And just remember, as we're going through this, I'm recording every day, and so they're getting posted to the practice playlist, which is on Google Classroom. So if you're working on mastering and you're like, oh, I missed this part of the example, it is there, so you can fast forward. They're on YouTube, so you can fast forward to whatever spot you need to. So example 14. Example 14 is like number 26 on mastering. And this is like number 26. So the acid dissociation constant for benzoic acid. Acid dissociation constant is Ka. So this would be like what a quiz or a test question would look like, where they give you Ka in the problem. So the acid dissociation constant for benzoic acid is 6.5 times 10 to the negative fifth. So Ka is 6.5 times 10 to the negative fifth. Calculate the equilibrium concentrations of H3O plus, the benzoate ion, and benzoic acid. Remember that H3O plus and H plus are used interchangeably. The initial concentration of benzoic acid is 0.050 molar. So they gave us an initial concentration. We don't have anything for the ions initially. All they told us initially is that we have our acid. They didn't give us any other information except for the Ka. Our goal is to find each of these equilibrium concentrations. That's our goal. So if they don't give us anything else, think back to what we did before, we used X's. So if this is my reactant, because it's the only one I'm starting with, I'm gonna have minus X. And because my ratio is 1 to 1 to 1, if I'm subtracting X on the left, I'm gonna add X to both of the substances on the right. So my equilibrium is 0.05 minus X, X, and X. So we've done this before. We did this before, and we used our Ka, well, at that point we used Kc, to solve for X. Now we're just going to use Ka. So just like before, let's write the expression first. The Ka expression is the H plus concentration times C7H5O2 minus concentration for HC7H5O2 concentration. They're all aqueous. They can all get plugged into the K expression. So now I'm going to just plug in values. So they gave us Ka. They said that Ka is 6.5 times 10 to the negative fifth. I have x times x on the top and 0.05 minus x on the bottom. Now, initially you look at this, and if I wanted to solve for x, looking at this right away, what does it look like we would have to use? Quadratic. However, we are going to use a shortcut to prevent the use of the quadratic. Now, if we use this shortcut, you have to make sure that you are writing down that you are using the shortcut. What I mean by writing it down is just put a little star and say, assume x is small. If we make the assumption that x is small, what we're saying is that x is so small that when we subtract it from 0.05, it's not going to make a difference. By saying that x is small, we're saying that when we subtract x, it's going to be so small that it's still going to be 0.05. So when we assume x is small, that allows us to neglect the minus x. That allows us to ignore this minus x part. But you have to write down that you're assuming x is small. All right, so then we can ignore the minus x. So if we do this, right now we can just solve for x. So 6.5 e negative 5 times 0.05. I'm going to take the square root. X is 0.0018. Oh, 2 sig figs. Well, there it is. X is 0.0018. Now we can make this assumption when K, so I'll just make a note over here. Assume x is small when K is less than 1 times 10 to the negative fourth. So because Ka was less than 1 times 10 to the negative fourth, we can make this assumption. The reason that that's kind of the threshold for this assumption is because by making this assumption, we're assuming that this weak acid dissociates or ionizes less than 5%. If it ionizes more than 5%, we can't make the assumption. So if x is 0.0018, right, we can't just box x and say there's my answer. We need to solve for what is in the equilibrium row. So let's plug it back in. So 0.05 minus 0.0018, 2 sig figs, is 0.048 molar. Notice how it barely made a difference. Then x, 0.0018 molar, 0.0018 molar. Here are our answers. We solved for the equilibrium concentrations by using the Ka expression. If they don't give you anything else for an ice table, you'll use x's. We can make the assumption that x is small so that we can ignore the minus x, prevent the quadratic. And then once we solve for x, just don't forget to plug back in. Any questions on this before we do the last example? So this actually gave us the Ka, so we didn't need Appendix D. The usefulness of Appendix D is going to be, for an example, like 15. Right, where in 15, they don't give us the Ka. They tell us that they're in Appendix D. So if on mastering, you're trying to solve for an equilibrium concentration or something like that, and they don't give you a Ka, use appendix D. So example 15 is like number, oh, there aren't like a lot of them, but I didn't have a number written down for 15. So example 15, calculate the pH of the following solution. 0.175 molar hydrozoic acid, HN3. So calculate the pH. So if I want to calculate the pH, that means I'm going to need to solve for H plus concentration. And even more, I need to solve for the H plus concentration at equilibrium. Because if we want to calculate the pH, that's negative log of H plus, but it's negative log of H plus at equilibrium. So right now, they gave me the initial concentration of the acid. That's all we have initially. We don't have any of the ions, we just have the acid. So they didn't give me anything else. Since I'm solving for pH, I should have Ka. Since I'm solving for pH, that means I'm going to need the Ka. This is where we use appendix D. So if you look at appendix D, around the front page, you can find hydrozoic acid, HN3. About halfway down, we see that the Ka is 1.9 times 10 to the negative fifth. That is where appendix D is important, is if we need a Ka value, we find it in appendix D. So again, if I'm solving for pH, that means that I need this value. I need the equilibrium value of H plus. They didn't give me anything else for the ice table. They didn't give me anything else for the ice table. I'm going to use X's. So minus X plus X plus X. So 0.175 minus X, X, and X. And now I have equilibrium information. Well, I also have Ka. When you have X's in the ice table, you should have a Ka value. Again, let's stay in the habit of writing the expression first. So H plus concentration times N3 minus concentration over HN3. Then we can plug everything in. Ka is 1.9 times 10 to the negative fifth. H plus is X, N3 minus is X, over 0.175 minus X. Again, you look at this and you're like, oh, quadratic. But because K is less than 1 times 10 to the negative fourth, we can assume X is small. But if you make that assumption, you have to write it down. When I assume X is small, I can ignore the minus X on the bottom. I'm assuming X is so small that it's not going to change that bottom number by much. So 1.9, E negative 5 is 0.175, square root. X is 0.00, I can use 3 sig figs, 182. There's X. Now, I need to think about what X is. I want the problem I want me to solve for. This is why I underlined what I needed to help me. I underlined the H plus concentration. Well, the H plus concentration is 0.00182 molar. Now, why is that helpful? That's helpful because I want to calculate the pH. The equation to calculate the pH is on your equation sheet. Negative log of the concentration of H plus. So take the negative log of 0.00182. Get 2.739. If we do 3 sig figs based on this, pH is 2.739. So notice that it's a little bit different for weak acid. Last week, when we looked at strong acids, we just used the concentration of the acid, but that's because it completely ionized. When you're at equilibrium, it's at equilibrium between the acid and the ions, so you have to use an ice table. So if you want pH, just remember that that's the H plus concentration. We're going to go through question 16 or example 16. I can actually tell you exactly what page this example is on. This is on page 18 of the notes. So example 16 is on page 18 of the notes. So I'm going to back up a little bit so that you can see. So example 16, if you want to make yourself a note, this is actually like numbers 28 and 34 of mastering. So this is like 28 and 34 of mastering. And example 16 is actually asking us to calculate the percent ionization. So it says calculate the percent ionization of 0.4 molar hydrozoic acid HN3 solution. The Ka for this acid is 1.9 times 10 to the negative fifth. So a few things. The first thing that I want you to do is I want you to write the acid dissociation equation. Right? You do not have this written in your notes. I was trying to write some extra information to save us some time as we were working through these examples. So you have the question in your notes. What I want you guys to write down is the acid dissociation equation. So this is a weak acid. HN3 is a weak acid. Weak acids exist at equilibrium. So hydrozoic acid is at equilibrium with H plus and N3 minus. And I even put the states of matter just so that we remember that weak acids are aqueous and ions are aqueous because they come from solution. Now, the problem is asking for percent ionization. So I'm going to underline percent ionization. I wrote the equation for percent ionization down here. Again, to save us a little bit of time. Somewhere around example 16, I would not recommend right underneath the equation because you'll notice that I have an ice table set up and ready to go. But somewhere, write down the percent ionization equation. This equation is not on your equation sheet, but you need to be able to use it. So percent ionization is how much does the acid ionize? What percent of the acid actually ionizes? Now, for weak acids, it's usually less than 5%. So it's going to be somewhere less than 5% for a weak acid. Strong acid should be 100%. But when it wants percent ionization, the way that we calculate percent ionization is the H plus concentration at equilibrium. So here's where our ice table comes in. We need something at equilibrium. So H plus concentration at equilibrium divided by the initial concentration of the acid times 100. So if we think about what we have right now, I want to calculate percent ionization. So I'm just going to do percent ion just to shorthand. Right now, based on the problem, calculate the percent ionization of a 0.4 molar hydrozoic acid solution. I have the initial concentration of the acid. I have the initial concentration of the acid. What I don't have and what I need is the H plus concentration at equilibrium. So in order to finish off this percent ionization calculation, I need H plus at equilibrium. I need that value right there from the ICE table. So let's fill in the ICE table and let's see how we can find delta H plus. So this is a 0.4 molar hydrozoic acid solution. So the initial concentration of the weak acid is 0.4 molar, right? 0.400. That's from the prompt. Nothing about ions initially, so those are 0. Now, it doesn't say anything else. It doesn't give us pH. It doesn't give us anything else about equilibrium. All it gives us is Ka. So we're going to use X's. So we will subtract from the weak acid. We will add to the H plus and N3 minus side. It's a 1-to-1-to-1 ratio. So it's just minus X plus X plus X. So for my equilibrium row, I get 0.4 minus X, X, and X. Now again, my goal is to solve for what I underlined. My goal is to solve for the H plus concentration at equilibrium so I can plug it into percent ionization. So over here off to the side, I'm going to use the Ka expression because Ka gives us information at equilibrium. That's our equilibrium constant. So Ka, I'm going to write the expression first. Products over reactants, everything is aqueous. So H plus N3 minus over HN3. Ka is 1.9 times 10 to the negative fifth. H plus times N3 minus, that's X times X, so X squared, over 0.4 minus X. Now remember, when you look at this, you're like, oh, this looks like the quadratic. But if K, right, if K is smaller, if it's less than 1 times 10 to the negative fourth, we can neglect X. We can assume X is small. So since this is a smaller number than 1 times 10 to the negative fourth, right, negative 5 is less than negative 4, we're going to assume X is small. If you assume X is small, you have to write it down. So I'll just make myself a note up here. Assume X is small. So we're assuming X is small. What that does is that allows us to ignore the minus X. We're assuming that X is such a small value that it's not going to impact the initial concentration of the acid. So now we have 1.9 times 10 to the negative fifth equals X squared over 0.4. So now I'm going to use my trusty calculator. 1.9 e negative 5 times 0.4. I'm going to take the square root of that. X. We'll use 3 sig figs. 0.00276. 0.00276. There's X. Now you have to think about what X is and what you're trying to find. That's why I always like underlining information from the ICE table. When I underline this, that tells me X is what I was trying to find. 0.00276 molar. Now I'm going to go back up. Percent ionization. My final answer is percent ionization. Well, see, I started the percent ionization equation down here. I needed X, I needed H plus so that I could find percent ionization. So what percent ionization is showing us is it's showing us how much H plus we have at equilibrium. So once this weak acid reaches equilibrium, how much H plus do we have compared to how much acid we started with? That's percent ionization. So I'm going to do 0.00276 divided by 0.4 and multiply by 100. I guess if we keep 3 sig figs, 0.690 percent. Percent ionization has the units of percent. My box got a little crooked there. 0.69%. That means that this weak acid only ionized 0.69%. So if you have 100 molecules, only 0.69 of them will separate into their ions. The other 99.3%, right? The other 99.3 molecules stay together as weak acid molecules. So this doesn't ionize very much. So that's looking at percent ionization. And something to keep in mind is the higher the percent ionization. So I'll write it over here. The higher the percent ionization, the stronger the acid. So the higher the percent ionization, the stronger the acid, because think about it. Strong acids ionize 100%. Strong acids ionize 100%. So the higher the percent ionization, the stronger the acid will be. This is a pretty weak acid. It only ionizes 0.69%. So that's looking at example 16. As you look through example 16, are there any questions? So again, we were using the ICE table for the weak acid to calculate something at equilibrium. We were calculating H+. So yesterday we looked at how we could calculate pH, which needed H+. But instead of pH, we were calculating percent ionization. Again, make yourself a note. Percent ionization is a formula that you need to know, but is not on the equation sheet. So percent ionization is H+ concentration at equilibrium divided by the initial concentration of the acid. Any questions? So for example 17, you flip in your notes to example 17, it looks like this. It says citric acid, which is present in citrus fruits, is what's called a triprotic acid. Tri means 3, protic for proton. Triprotic has 3 protons, 3 H's. It says calculate the pH of a 0.050 molar solution of citric acid. And you see that you have 3 equilibrium equations here. If you actually look at Appendix D, right, in Appendix D, citric acid has 3 Ka values. And if you look at citric acid, it has 3 Ka values. The 3 Ka values represent each H that's being removed. So Ka1 represents the first H being removed. Ka2 represents the second H being removed. Ka3 represents the third being removed. When we have a polyprotic acid, whether it's diprotic or triprotic, we typically just assume that the first ionization is the most important. And you have this statement already written in your notes. Right? In your notes, it already says to calculate the pH, assume initially that only the first ionization is important. Typically, the first Ka is the largest Ka. That's the one that's most likely to occur. So we're only going to focus on the first Ka. We're only going to focus on the first ionization, the first H+ being removed. But I do want to point out how only one gets removed at a time. It's not going from H3, C6H5O7, to C6H5O7 3- at once. You have one H that's being removed at a time. So what I want you to do is write the acid equilibrium equation for the first ionization. So it's just this first ionization equation we're just rewriting. The reason that we're rewriting it is because it's a weak acid. we have to do any calculations with a weak acid, we're going to need an ice table. Now, if you ever look at any of the College Board like practice videos that they put up, or other teachers, like if you find other teachers' explanations on YouTube, sometimes instead of ice tables, you'll hear them say rice tables. Well, we actually do that already because the R means reaction. So when we make our ice tables, we make them like this with our reaction at the top. Some people call them rice to make sure that you put the reaction. So just in case you ever are looking at anything and you hear them say rice, it just means reaction. So our goal is to calculate the pH. Our goal is to calculate the pH of this weak acid. Now, because it's an acid, I'm going to look at the equation, and I remember that pH is negative log of H plus. pH is negative log of the concentration of H plus. But the pH uses H plus at equilibrium. So I actually need to solve for this spot in the ice table. So then we plug in what we know. Even if you can fill in the ice table, it's a very good strategy to always use an ice table. So 0.05 molar, 0, and 0. They didn't give us anything else. They didn't give us pH, which tells us H plus at equilibrium. They didn't give us anything else to plug into the ice table, so we need X's. So the acid is going to decrease by X amount. H plus and H2, C6, H5O7 minus both increase by plus X. Remember, the change row is based on the stoichiometry. They're all 1 to 1 to 1. So we get 0.05 minus X, X, and X. Now you get to this part, and it's important to think about, okay, well, I have these variables at equilibrium. What can I use if I have equilibrium? Well, we have our Ka. We are only assuming that the first ionization is important, so we're using the Ka that goes with this equation. So if I write the Ka expression off to the side, H plus times H2, C6, H5O7 minus over citric acid. Now we plug in what we know. This is an equilibrium constant. We need equilibrium concentration. So Ka for the first ionization, 7.4 times 10 to the negative fourth times squared over 0.05 minus X. If you're making the assumption, make sure to write it down somewhere. Assume X is small. Because we assume then that that minus X does not play a role in changing the initial concentration of the acid. 5 square root. I get my X value, 0.006, two same things, 0061. There's X. Now I'm going to pause and I'm going to say, okay, what is X? Why is X important? Well, X is 0.0061. That's the H plus concentration. That's the anion concentration. And I look back and say, okay, I need pH. pH is negative log of H plus. Negative log of 0.0061. So negative log 0.0061. And the pH is 2.21. Now, I'm going to just look at that. Citric acid is a weak acid. We were focusing on Ka values. So it makes sense that we have a pH of 2.21. So this is just like what we've been looking at before. We looked at calculating pH a couple days ago. But the difference here is that we had a polyprotic acid. In this case, it was triprotic. When you have an acid with multiple protons, we are going to always assume that only the first ionization is important, right? Just the first ionization. Any questions on this one? But I think the bell's going to ring in just a second. Oh, yeah.
How do you know to use the first equation?
So just when we look at polyprotic acids, we're always just assuming that the first one, because the first one is usually the largest Ka, we're usually going to use the largest value of Ka.
Oh.
So whichever Ka is the largest, that means that that's the ionization that happens most often. And so that's the ionization that we're going to use. Typically, it's almost always the first one, which is why we use that. Yeah. So, example 18. If we read through 18, now we notice that there's something a little bit different. Because it says calculate. All right, it says calculate the molar concentration of OH minus. And it says that we have hydrazine. Now we're going to deal with the base. Okay, so if you need to use the restroom or get up, walk around, we're going to take a quick break right here. We have this example, which is math, and then we have two more that are conceptual, and then you'll have some time to work. So this will be the one that will probably take us 5 minutes, 6 minutes. The other two won't be as long. So if you want to walk around, take a break, and we'll go through this.
Take them on a walk.
Yeah. Hi. Gold group, I haven't seen you in like a week.
I know, I'm sad.
I mean, I know there's so many of you that are here on gold days. We had 3 on, what day? What day was that? Friday? Friday. We had 3.
Yeah, Friday.
Yeah.
You have a good number today.
Yeah, I know. Yeah, I brought the water bottle today. Hold on. I haven't drank any though, so don't judge. I was drinking my coffee.
How much do you think you drink out of that?
On what's today? Wednesday? On Monday, I drank the whole thing.
Is it hard to drink that whole thing?
See, here it is. It's harder during school. Yesterday, I just forgot about it because I was drinking coffee. But it's just hard to drink during school because then I have to go to the bathroom all the time. So. But I drank this whole bad boy on Monday. Finished it by 8 o'clock. It's fine. See, I'll bring it tomorrow. Then you guys can really see it. See, on Google Meet, it just looks like a normal water bottle. It's not.
All right, listen to this. I saw someone walking out of practice with that water bottle.
This one.
Yep.
So you see how big it is.
I already saw it, yeah.
It's massive.
It's huge. It was like this, she had to use 2 hands to carry it.
I know. And there's this strap, but when it's full, it's heavy. It's like a baby.
I guess just keep chugging outside.
I know. Has times. That's how I know I'm behind. I'm supposed to be right here.
You drink one of those every day?
So I just got it on Friday.
That's a huge one.
Yep, it's a gallon. I drank the whole thing on Monday. I'm going to try to drink the whole thing today. I'll just carry it around. I don't take it to study hall because I don't know anyone in study hall, and they already are like, who are you? So,
If you would bring a water bottle in the Audion and then everybody's just.
Just like walk around with it. Around the hallway.
I did the 8th period on Monday.
Wait, have you seen the office?
It's so-
How Dwight has that backpack? Like, you need to
I
go into
mean,
the-
I could just carry it. I should just do that. It's fine. I stay very hydrated. And actually, when I drink all of that on Monday, like I actually go home and like snack a lot. I wasn't even hungry because I drank a whole gallon of water.
Where'd you get that? I need to-
Amazon.
Okay.
I opened the Amazon box because we were talking about it on Friday. That's why Kaylin and Mara, I was like saying, oh, I'm getting like this water bottle. It's gonna be awesome. And I opened the Amazon box on Friday, and I about fell on the floor laughing. I pulled it out of the box, and I was like, what? And I sent them a reminder, like holding it next to my head. It's bigger than my head. But it's
You
fine.
need like a half gallon so you can fill up water.
So like the cup that I usually bring is 1/4 of a gallon. It's 32 ounces. That's 1/4 of a gallon. But like when I would be here, I would drink it all, and I'm not gonna use the water fountains here. So I was like, well, I'll just get this water bottle. I thought it was less massive, but it's not. I know. See, it's fine. Okay.
Yeah, this is what's funny. You know who we could really see with one of those? Mr. Reader.
Yeah, I know. I'm kind of upset that I have something that makes you think of Mr. Reader.
Start talking about like beer and like elm trees.
It's like this is my venti cup. Next to this water bottle is insane. Venti cups are not small. It is compared to that water bottle. It's fine. It's okay. So, for this example, example 18 is actually like numbers 31 and 32 on mastering. So if you want to make yourself a note, 31 and 32 on mastering. This is looking at a weak base. So in this example, it says calculate the molar concentration of OH minus ions. So my answer needs to be OH minus ions and a 0.050 molar solution of hydrazine. Now, one way to know that this is a weak base is that when you have substances that have NH2, so when you have this NH2 group at the end, that's called an amine, A-M-I-N-E. It's an organic functional group. But amines are bases. They're weak bases. Now, the other reason that I know this is a weak base is because they gave me the Kb value. Kb means we're dealing with a weak base. And then it also asks for the pH. Now, it's important to remember if we're dealing with a base, pay attention to what we're calculating. So the first thing that we need to do is we need to write the equilibrium equation like we do with acids. Now with bases, we need to make sure to include water. And the reason that we need to make sure to include water is because bases need to accept a proton. So I think it was your question yesterday on whether you need to include water or not. With acids, it's up to you on if you want to do plus H2O. If you do plus H2O, then instead of H plus, you're going to have H3O plus, right? And that means the same thing. With bases, you want to include H2O because that's where you're getting the proton from. If this is a base, water has to be the acid. And so it's actually going to accept a proton. Once hydrazine accepts a proton, it's going to become H2N NH3 plus. Now, if you did H3N NH2 plus, I would accept it. Mastering, if you're doing a question like that on mastering gets a little finicky because it wants you to put the plus right next to where the positive charge is. The positive charge is located where there's 3 H's, so that's why we write it like we do for bases. And then once water loses the proton, it becomes OH minus. So notice why hydrazine is a weak base. Because when it's with water, it produces OH minus in solution. So because we're dealing with something that's weak, we're going to need an ice table. Whether it's a weak acid or a weak base, we need an ice table. Now, here's what I want to make sure that we do. We need to focus on what the question wants. Once I set up the ice table like this, I'm going to go back and look at the question and say, okay, what does it want me to find? Well, one of the things is the concentration of OH minus. If it's asking for concentration of OH minus, it wants OH minus at equilibrium. But it also wants pH. Now, I just want us to think really quick before we have numbers here. If I take the negative log of the OH minus concentration, what am I finding?
POH.
POH. When I take the negative log of the OH at equilibrium, that's POH. It wants me to find pH. So how do I find pH from that? Right, 14 minus POH. And if you're like, well, I don't know, I don't remember. Take a look at your equation sheet. It has 14 equals pH plus POH. So I just wanted to write that down initially so when we have numbers, we're remembering what we're finding. So let's look at what we have. So we have a 0.05 molar solution of weak base. I'm going to put an X through H2O. Why can I put an X through H2O? It's a liquid, right? Liquids do not affect equilibrium. And then because it doesn't say anything else about initial, there's 0. Now it doesn't say anything else. So I'm going to use X's. Plus X. Plus X. Now because this is a base, we're using the KB expression. And so that is our conjugate acid, H2N, NH3 plus, times OH minus, over H2N, NH2. No water. This water's a liquid. So now they gave us the KB value. 1.3 times 10 to the negative 6 is X times X over 0.05 minus X. Again, if you make the assumption, you have to write down that you're making the assumption that X is small. You know, don't simplify, assume, because there are some great stories about when people assume X is small and they try to shorten assume. So when we assume X is small, that minus X gets ignored. So 1.3 e negative 6 times 0.05. You get 6.5 times 10 to the negative 8. You take the square root of that to solve for X. 2 sig figs, so 2.5 times 10 to the negative 4. I notice that I underlined X over here. 2.5 times 10 to the negative 4 is the molarity of OH minus. Now, I'm keeping it in my calculator, so you might round a little differently, which is fine. When I do the negative log of OH minus, we are finding POH. Here's where labeling becomes very important. Oh wait, 2 sig figs means 2 decimal places. So 3.59. This is where writing this has now become helpful because now I can just do 14 minus 3.59, 10.41. Now you can ask yourself, does it make sense that the pH is 10.41? Well, we're looking at a base. So yeah, it should make sense. It should make sense that the base has a pH of 10. Bases should be above 7. Now, I just want you to write this equation down. We're not going to actually do this calculation. But if we focus on percent ionization, I want to just look at how this is similar but a little bit different from an acid. Percent ionization means the same whether you're looking at an acid or a base. You're looking at how many ions do you have at equilibrium compared to the initial amount. So if we're looking at the percent ionization of a base, it's going to look just a little bit different. Because a base means we're focusing on OH minus. So if a question says, what's the percent ionization of the base? We're going to compare the OH minus concentration at equilibrium to the initial concentration of the base times 100. So the percent ionization of a base is just slightly different because we're focusing on the OH minus concentrations at equilibrium compared to the initial of the base. Where an acid was H plus at equilibrium compared to initial of the acid. And again, we're not going to actually calculate, but I just wanted to focus on that equation. Any? Yeah.
Why can't you like take an H plus from the H2 and H2 and move it over to the H2?
So since they give us the Kb value, they're telling us that this is a base.
Okay.
Now, in terms of why this won't act as an acid, that has to do with the Lewis structure, with the electronegativity, with the strength of the bonds. But because they gave us Kb, they're telling us that it's a base, which means that water has to be the acid. Yeah.
So if we flip to page 19, right? Flip to page 19. Page 19 has example 19 at the top. So this example we're going to do right on the screen. So for this example, it says, although the acid dissociation constant for phenol, so acid dissociation constant, this is Ka. So although the acid dissociation constant for phenol, so Ka, is listed in Appendix D, the base dissociation constant for the phenolate ion is not. So again, what this is saying is that the acid dissociation constant, Ka, is given in Appendix D. But Kb for the conjugate base, because if we take a look, the phenolate ion is the conjugate base of the acid. So Ka for this acid is given, but Kb is not. And we can actually take a look. So let me pull Appendix D over so that we can take a look at Appendix D with, all right, so let me zoom in a little bit. All right, so on Appendix D, and if you have Appendix D, you can see on yours as well. I'm just pulling it up on the screen. In Appendix D, on the front page, these are all the Ka values. So notice here, phenol, we have our Ka value. So for phenol, we have our Ka value 1.3 times 10 to the negative 10. But if we flip to the back page where the Kb values are, right, table D2 has Kb values. Notice that that phenolate ion is not there. So Ka is given here, but we don't see the Kb value in Appendix D, and it wants to know why. So the reason that we don't see every Kb value in Appendix D is because for any conjugate acid-base pair, Ka times Kb equals Kw. So again, when you have a conjugate acid-base pair, so phenol is a weak acid. It's telling us it's a weak acid because it's talking about the acid dissociation constant. So phenol is a weak acid. The phenolate ion, notice how it looks similar. The only difference is that this has one less H+. This is the conjugate base. So for any conjugate acid-base pair, Ka times Kb equals Kw. This equation is on your equation sheet. Ka times Kb equals Kw is on your equation sheet. So if you have the Ka of an acid, you can find the Kb of its conjugate base by using this equation. We're assuming 25 degrees Celsius unless they tell us otherwise. So unless they tell us that it's at a different temperature and they give us a different Kw, we assume that it's 1 times 10 to the negative 14th. So then part B says calculate the Kb for the phenolate ion. So in part B, let's use the equation. So Ka, we just said, was 1.3 times 10 to the negative 10. Right, that was in Appendix D. So Ka is 1.3 times 10 to the negative 10. We're solving for Kb. Kw is 1 times 10 to the negative 14th. So if we want to solve for Kb, we manipulate the equation. Kb is Kw over Ka. We assume Kw is always 1 times 10 to the negative 14th. We assume we're at 25 degrees Celsius. So if we do Kw, 1 times 10 to the negative 14th, divided by our value of Ka, and again, this value of Ka came out of Appendix D. So this value of Ka came right out of Appendix D. When we divide the two, our Kb value is 7.7 times 10 to the negative 5th. So if I do Ka times Kb to check my answer, it's going to be close to 1 times 10 to the negative 14th. Maybe a little bit off because of rounding, but it's going to be close. So if you have Ka of a weak acid, you can find Kb of the conjugate base using Ka times Kb equals Kw. Then part C, is the phenolate ion a weaker or stronger base than ammonia? So is the phenolate ion a weaker or stronger base than ammonia? Now, when you want to compare bases, you want to compare the strength of bases, you're going to compare the Kb values. So you want to compare the Kb value of phenolate, which we just calculated here, to the Kb value of ammonia. And you can find the Kb value of ammonia in Appendix D. So if you have Appendix D, you flip to the back. Your Kb values are in the table up at the top, right? Table D2. Take a look at Appendix D and see what the Kb value is for NH3. So you're comparing, right now you're looking for the Kb value of NH3. You should see that it's 1.8 times 10 to the negative 5th. So when we want to compare bases, we need to compare the Kb values. If you want to look at the strengths of acids, you would compare Ka values. Because the higher the K, the more it dissociates and the stronger it is. So if we're comparing Kb, the Kb for phenolate is 7.7 times 10 to the negative 5th. We just calculated that in part B. Kb for NH3 is 1.8 times 10 to the negative 5th. So notice they're both times 10 to the negative 5th. So we're just going to compare the numbers in front of the scientific notation. 7.7 compared to 1.8. 7.7 is a greater number. So the Kb for phenolate is larger than the Kb for ammonia. That means that phenolate is a stronger base. So again, something that you can write down next to this example is that the larger the value of K, the more it dissociates, and the stronger the base or acid. So the higher your value of K, the more it dissociates, because that's what this represents, products over reactants. So the larger your value of K, the more products you have, the more it dissociates, and the stronger the acid or the base. Okay, so that's comparing Ka and Kb. Right, comparing Ka and Kb, looking at how we can calculate one if we have the other, and then how we can actually compare the strengths. So we can compare the K values. So either Kb for bases or Ka for acids. We can compare those values and we can see which one is stronger, because the larger the value of K, the more the substance dissociates, and so the stronger either the acid or the base. Okay, any questions on example 19? Because we're going to kind of switch to video 7.4. Okay, let's see. Yes, question. The top value in part B. So this is Kw. So remember on your equation sheet, Kw is 1 times 10 to the negative 14th. That's the auto-ionization of water. So that's a constant. Kw is a constant. 1 times 10 to the negative 14th is a constant. Yeah, it's always the same.